very happy to be able to present this. Thanks for inviting me to your seminar, Atul, to have the chance to talk about this work that I was working on together with Mathilde, who's here, and Sinisha and Ivan, about bounding the asymptotic quantum value of all multipartite non-local games. So in the beginning, I'm going to go through a little bit what these different words mean. So I'm going to talk about what's a non-local game, how we compile them, why do we care about the multipartite case, and what's the quantum value, and then I'll get to the technical part. Okay, so quick recap on non-local games for those that are not familiar with them. So this is these are some kind of protocols that are. Can you see my my cursor, by the way? Can I use it to point at things?
Yes.
Yeah.
Okay, perfect. Thanks. So these are really useful because they are a tool to kind of tell classical and quantum worlds apart, or people have been studying other worlds of correlations as well. And the correlations that people study are those that are arising in a situation where two or more parties are space-like separated from each other. They get separate inputs, produce outputs, and during the course of this protocol, they cannot communicate. However, before the protocol starts, they are allowed to share arbitrary information and decide on their common strategy. In the quantum case, share an entangled state potentially. And why people have been studying this, as I mentioned, is that depending on whether Alice and Bob behave classically or quantumly, or even post-quantumly, the correlations that they can generate are different. So as depicted here on the right side, the green square would be classical in like a special case. The green square would be classical correlations, and then the yellow set outside would be the quantum ones, and then the red square would be non-signaling correlations. And so now a nice thing, how to make some kind of like a proof out of it, a protocol, is that they can play a game, which essentially means that we check a certain condition on the outputs of these two parties, on their inputs. So there's, for example, the most famous one probably, which is the CHSH game, in which the parties need to generate an output such that the XOR of the two output bits is equal to the AND, or the multiplication of the two input bits. And classically, one can show that they can win this at most with 75%. Quantumly, we can actually go beyond, so we can go to around 86%, 85, 86%, and so we can basically tell them apart, because we know that if players win with more than 3/4 probability, they can be acting classically. And then no signaling goes even beyond, and in this case, they can win with probability 1. Okay. So one thing that I should quickly mention, also because it's getting important later, is that the space-like separation between the parties can be modeled in different ways. So probably the most common way how people think about this in quantum information is tensor products. So Alice and Bob have separate Hilbert spaces in which they act. Their shared resource lives in the tensor product of these Hilbert spaces, and operations that Alice performs only act on the left register, Bob only on the right. There's another way of capturing some kind of separation between the parties, which is requiring that all of the operators are commuting. So the operators that describe Alice's system and the operators that describe Bob's system, they could be acting on the same registers, but they need to be pairwise commuting. Now, it turns out that naturally, if we have tensor products, then these are also commuting because they're acting on different registers. And so this is a special case of the right side. But there are situations in which they are not the same. So in finite dimensions, these two are the same. So we can always turn commuting operators into tensor product strategies. But in infinite dimensional systems, this might not be the case anymore. And there is the celebrated MIP star equals RE result that actually also points at the fact that these are different in specific cases. And this will play a role later. So people have been looking at removing the space-like separation Alice and Bob in these non-local games, and between the parties in the non-local game, for several reasons. For example, it could be difficult in some implementations to actually enforce this. Also, for cryptographic applications, it can be advantageous to just basically treat them as a single party without any kind of separation between what Alice and Bob can do and how the information about their inputs flow. So to remove the separation between the parties, this using cryptography, the simplest possible model is the one on the right that one could think of. So just encrypt the inputs, give them to the prover. The prover, we use some kind of homomorphic encryption that allows the prover to act on these ciphertexts. They will output the responses. But it turns out that in this case, actually, the prover can do correlations that might not be possible on the left side. Especially, people have been showing that this prover here can generate no signaling correlations on the input, even though on the left side we might be restricted to classical or quantum correlations. So this doesn't work. So in this paper by Kalai and others a couple of years ago, they proposed to fix this problem introducing sequentiality. So the idea was encrypt the input again to the first input actually, but don't give the second input at the same time, but rather wait for the prover to return the first response before giving them the next input. And it turns out that in this case, actually, we don't even need to encrypt the second input. It's sufficient if the second input is sent in the plane to the prover. So in some sense, you can see that here, this like space-like separation is somehow moved into a temporal separation through the sequentiality. So we can somehow still talk about, part of this prover, which is Alice, part of this prover, which is Bob. And so this compiler was actually proposed for all player games, for all multiplayer games. So that means if here on the left side we have more than 2 players, then we can do the same thing on the right side, where the challenges are sent one by one. Every time before the next challenge is sent, we expect the previous answer. And all of them are going to be encrypted, except for the last input. The last input does not necessarily need to be encrypted. So just maybe a quick word about what this cryptographic functionality is that the compiler relies on. So this is quantum fully homomorphic encryption. And the purpose of this is that the prover can actually operate on the encrypted information that the verifier sends to them. So here on the right side, if we want to be able to reproduce strategies that the prover can perform in the non-local case previously, where they have access to the plain text inputs, we somehow need to be able to take whatever operations Alice is doing here on the left and turn them into something that Alice can do on the encrypted information on the ciphertext on the right side. And well, the functionality that does that is homomorphic encryption. And in our case, actually, we require this homomorphic encryption scheme also to be able to handle auxiliary quantum input, which is going to play the role of the entanglement or that the parties shared in the non-local case. So the non-local case, they will have potentially an entangled state, apply some measurements on this, and on this here on the right side, Alice will prepare potentially some quantum resource, feed part of it into her own evaluation of the measurements that she's applying on the ciphertext on the encryption of X, and give the rest of the resource to Bob, who can then implement his normal strategy. And naturally, we want that the scheme that we're using, and that is in the end what the compiler, the security of the compiler is going to rely on, is the security of the QFAG scheme, which essentially means that the prover here in this case, when they have access to an encryption of X, they will not be able to infer any information about X. So previously, it was shown that this compiler is classically sound for all games. So that means for no matter which non-local game you compile, no matter how many players it has, classical provers in the compiled game will not be able to do substantially better in any of these games than classical provers in the non-local version. And this is something that relies on the security of the QFAG scheme. Another thing that was shown in the original KLV white paper is quantum completeness for all games, which means that whatever quantum provers can do in the non-local setting, they must also be able to do in the compiled setting. And these two are already sufficient to show that the protocol at least preserves quantum classical gaps. So if there is a quantum classical gap here in the non-local case, then this will also be translated to a gap in the a gap of essentially the same, at least the same size, also in the compiled case. Now, this doesn't say much about how much better quantum provers potentially could do in the compiled game. So this is the question for quantum soundness that people have been looking at, and so there has been a sequence of work stints that focus on this question. People that were studying the quantum soundness, and first they showed that quantum soundness is actually given by the compiler for some specific bipartite games. Then there was another paper showing that quantum soundness actually holds asymptotically for all bipartite games. And so the missing piece at this point is is quantum soundness preserved also by this compilation for multipartite games once we go beyond two parties? And that's essentially what we're doing in this work. Any questions so far? I take this as a no.
Yeah, so sorry, I can quickly ask one silly question, because I think I asked you before as well, which was that, do we really need int CPA, or is just indistinguishability enough?
Yeah, that is a good question, and I know that we've been discussing this already before. So this is a good question, and I'm not sure I know the answer right now. So int CPA is enough, whether it's sorry.
So just to clarify, the question is, do we need int CPA, or do we just need indistinguishability of some selectively chosen messages?
Yeah, I was asking like whether we need semantic security, or do we need like CPA? That's basically what I was asking. And I think semantic was probably enough, because that's what they used in the original papers. I was wondering if adding the quantum soundness bit requires stronger assumptions, or it's just for completeness.
I think it should be enough, actually. I think it should be enough. There's just one part where one needs to be a little bit careful, which is when we're basically when translating to the quantum regime. So when we start looking at quantum soundness, we need to rely on some block encoding tricks, and I'd want to be sure that we're not using it anywhere there, but I don't think so. But yeah, so I would carefully say probably not.
Okay, thanks.
Okay, yeah, thanks for the question. That's certainly something that at some point we should look into. Okay, so in this previous paper, I'm quickly going to recap now what they did in this previous paper, where they showed asymptotic quantum soundness for bipartite games, to then explain what we need to do to handle multipartite games. So their techniques essentially are saying start with a non-local game, apply the compiler to it, and you get what we have here on the lower left. Now we can think of this, because of its sequential structure, actually as a sequential game between two parties, where the first party is allowed to communicate a quantum state to the second. So just a quick reminder that we're talking about quantum soundness. So Alice and Bob here are acting quantumly, but because we can only guarantee that in a computational regime, they must be somehow computationally bounded parties. So on the right, now we have a sequential game, and we have some constraints that are coming from the security of the QFHE scheme. Then they're taken a limit in the security parameter, so they make the scheme more and more secure in some way, and I'm going to explain later actually what this formally means. But they're taking a limit in making the scheme basically ideal, the security of the QFHE scheme, and they get the situation where they have a sequential game where one party sends a state to the other, plus they have a form of no signaling condition, some form of preparation equivalences for the state that's communicated. And eventually they show that this can be mapped to the non-local game. Well, almost, because actually now we're falling back into a commuting operator strategy, which comes from the fact that in this transition here on the right side, we're going from finite dimensional to infinite dimensional strategies. So on the upper right, we're already having infinite dimensional strategies, and mapping this back to the non-local picture, we're kind of stuck with commuting operator strategies now. Okay, and eventually, like this, what they're showing is that if you start with any kind of compiled strategy here on the lower left, and you pull it through, you take this detour to the right and go back to the upper left, then asymptotically, whatever correlations that they can generate can also be captured on the upper left with commuting operator strategies. So why do we care to go from beyond two parties? It's kind of like let's say a natural extension, and it's I mean, even though it's not trivial.
Can I ask a question?
Yeah. Yes.
Sorry, can you go to the previous slide? So let's say here, I mean, yeah, like, I mean, so do they use some kind of a NPA kind of trick or something? Like, I mean, that because you're saying that, you know, like, I mean, it reduces to commuting a strategy, and I'm wondering, you know, like, I mean, it's not reducing to tensor. So, I mean, is it because somehow, you know, like in that blue arrow, NPA is inbuilt?
Yeah, that is a good question. So there is no explicit NPA hierarchy anywhere here in their techniques, and actually in our results there isn't either. There is let's say a hidden NPA hierarchy in some sense, because actually how this is treated, especially here on the upper right side, and also this blue arrow, these are algebraic arguments, and so these, basically the algebra in which these strategies are modeled, do give rise to an NPA hierarchy. And interestingly, this NPA hierarchy can be extended to the to this red limit, and handle also basically the imperfect case. But that has been a different work. So so this has been different work on them making this kind of security more quantitative. But to make it short, there is an NPA hierarchy somewhere hidden, or it gives rise to it, but we don't need to use it anywhere explicitly in the asymptotic proof. Okay, so somehow this is the point that I wanted to make, is that it's somehow a natural extension. We know we have classical completeness for all games. We have quantum completeness, we have classical soundness, and we have quantum soundness for all bipartite games. It's somehow natural to ask, does this also hold in the multipartite case? Especially because there are multipartite effects in quantum that we know of that are genuinely multipartite, that we cannot observe in the bipartite case. So people, for example, have been studying this phenomenon of post-quantum steering. That is something that occurs only when you have at least 3 parties. And there are other kinds of, things in, let's say, things in quantum information that get considerably trickier and more complicated once you get beyond 2 parties. Also, for example, in the study of entanglement. Okay, and there are more. So we might want to use this for crypto applications as well, especially for proof systems or for classical verification of quantum computations. And eventually, if we are having multiplayer games, keeping them space-like separated is obviously even more complicated than keeping 2 players space-like separated. And it's maybe also just not an assumption that we might want to make. So essentially what we're doing is we're trying to reproduce similar arguments in the multipartite case. But we need to have new tools, because basically all the green, the red, and the blue arrows, they're going to require more theory that adapts them to the multipartite case. Especially what we need to be able to handle here, which wasn't occurring in the bipartite case, is that there are going to be parties in these sequential scenarios, Bob here in the middle, which is neither a state preparation nor a measurement, but actually implementing quantum channels. So what Bob will have a classical input, a classical output, but also quantum input and output. So this will be modeled by quantum instruments. And in some way, our work can be understood as extending all of these technical tools to the case of quantum instruments. And then once we have that for quantum instruments, we can do similar arguments, go all this way around, and naturally extend to all K-player games, but just chaining basically these instruments. So once you handle the difficult case of Bob here in the middle, well, then you can see that, okay, Alice is just a special case of it, Charlie's just a special case of this. And actually, if we have, let's say, several Bobs, if we have more than 3 players, then we can compose the tools that we have for quantum instruments and get this working for all K-player games. Okay. So let's go through these errors one by one. I think on the compiler I can be quick because we already talked about this earlier. It's just to recap how the compiler looks now in the tripartite case. We need to encrypt the first 2 rounds of interaction. The last round of interaction can then be in the plane. So okay, now I want to spend a little bit more time on these other 3 arrows, because that's actually where most of our work went in. And okay, so this lower bit here is basically is the analysis of what are the constraints that are coming from the cryptography, as long as it's secure, on the correlations that parties can generate in such a sequential setting. Especially, what are the constraints that are imposed on the states that are being communicated between the parties. So the state that Alice sends to Bob, the state that Bob sends to Charlie, and also especially what are the constraints on how Bob can act on previous states and what he can output. So essentially, what are the quantum instruments? What are the channels that Bob can implement in the setting? So to this end, let's see how we can model the correlations that are generated. Basically, we have Alice that's implementing a state, then Bob that's implementing a quantum instrument that's acting on the state, and Charlie that's implementing a measurement of this. And what we get in the end, the probability, is the trace of all of these three operators. So by construction, we already know that that Charlie cannot signal to Bob, and Bob cannot signal to Alice, and Charlie can also obviously not signal to Alice, just because of the how time flows in the protocol, because of the sequentiality that the protocol already imposes. So basically, information cannot flow upwards in this case. Downwards, yes. In principle, yes. But the information that Alice can communicate about X is constrained by it being encrypted. So especially what we get from semantic security is that the information that Alice can signal in her state to Bob and to Charlie about X is negligible somehow in the security parameter that the scheme uses. Okay. So encryption somehow protects this information from not flowing downwards or only in a restricted way. However, it turns out it's not sufficient to only understand how which information can be extracted about X when Bob and Charlie are acting in the protocol, because these conditions essentially impose that the correlations that the parties generate are no signaling correlations. But actually what we want to do is we want to go beyond no signaling. So no signaling is fairly obvious because of the construction. But the question is, can we actually restrict further? In the end, we want to go back to correlations that are realizable in a quantum way, in a space-like separated quantum way. To do that, we actually cannot only look at which information about X can be extracted by the direct application of Bob's measurements, such as we can see here at the top, but what information is available to any kind of operators that can be represented as polynomials in Bob's measurements. And now, this here, you need to think of a little bit more as a formal inequality. I mean, this is mathematical because these polynomials might not necessarily be physical operations anymore. Especially these could be not Hermitian, or these could be not positive. So these might not necessarily be measurements here anymore, but there's going to be some kind of operators. We can define these traces, and so these quantities make sense. And actually, what we need is that this is also true. Now, if this is true, this is already maybe we can already start giving this like a little bit of an algebraic meaning. It's basically saying that information about X in the state is not accessible within the algebra that's generated by Bob's measurement operators. So in some way, we now get that these states actually, let's see, when seen through the lens of this algebra, these are roughly the same. Now, in our case, so we can do the same thing for, yeah.
So can I interrupt really
Absolutely.
briefly? So, the degree of the polynomial doesn't really come in here, right? There can be like unbounded degree. Like you're looking at the entire algebra, it's not restricted in any way, right?
Yes, so in principle, so we need this eventually for the entire algebra. The way how to do it actually is you fix polynomials of a certain degree, and then you show that this is true, this equation here is true, and this is actually, so this is going to be a negligible function in lambda, but these functions will depend on the degree of the polynomial. As long as you fix the degree, though, you get this negligibility of these two. And later, when we take limits, it will be sufficient that we fix the degree of the polynomial and exhaust the algebra like this. And that is actually, so this is, I think, the point where we are, losing the tightness of the correlation, in the sense that I think this is the point where we're going to commuting operator strategies. This is basically where we are, because essentially what we're doing here is we're saying we're taking the limits separately, right? We're fixing the polynomials, the degree of the polynomials, which essentially has something to do with the efficiency of Bob's operations, or let's say the complexity of an adversary. So we're fixing this. Then we take the limit in lambda, And I think this is one of the reasons why later we get into the situation where we have well, perfectly no signaling, but we're in this infinite dimensional case where now we just fall back to quantum commuting operator strategies. Did this answer your question?
Yes. I mean, I'll ask you more later, but for now, thank you.
Yeah.
So sorry, like, I have a very yeah, I think so. The question is that, I mean, so you're trying to construct all possible polynomials of, let's say, up to some degree, and there will be terms there, like which are not even Hermitian. So effectively, you are saying that any accessible information that the quantum adversary can have will not be able to distinguish between x and x prime, and hence, like you have the security. And so, but I mean, is it that you are trying to somehow provide security against, maybe, let's say, maybe more than a quantum adversary, like, I mean, because when it's like, it may not be even Hermitian, right? I mean, like,
True. So these operators here in green, they might not be Hermitian, so they don't correspond to measurements directly, but and that is actually part of the proof of showing this, is one can show that these quantities, these mathematical quantities, they can still be efficiently estimated using physical algorithms, using physical procedures.
Yeah, these work in these kinds of things, right? To estimate these objects, even though, like, by themselves they're not physical in a bigger system.
Yes, sort of through some post processing. Yeah, like I was just thinking that maybe it's like trying to give a soundness against, like something which is more than quantum, and hence you have the soundness against the quantum. But maybe it's exactly so, quantum. Yeah.
Okay. Yeah. So this is not what's happening here. So we're not doing anything. We're not allowing the adversary to do anything that's outside of quantum. Yeah. So even though these quantities here don't just directly correspond to physical operations, using block encodings of these operators, one can still show that they will correspond to something that can be physically estimated. And yeah, and as such, they somehow do capture. So looking at the algebra of these polynomials that is spanned by these polynomials and all of these quantities, we somehow do start talking about the information that is accessible to the adversary, the information that's accessible to Bob about x, or x prime in this case. And actually, for those of you that are familiar with the MPA hierarchy, this is somehow also very, very closely related to it. And that's why I was talking about the commuting operator strategies earlier, because somehow at the lowest level, so if we take only linear polynomials, so essentially we just have the direct measurements, this corresponds to a no signaling condition for the correlations between Bob and Alice. And if we now increase the degree of the polynomials, we're essentially getting something like an NPA hierarchy here. And as soon as we're exhausting the entire algebra, we know that this should converge towards the commuting operator value, towards a set of commuting operator correlations. Yeah. Now, we need to do a little bit more again in this case, because before, so on the left in the bipartite case, we had Alice's states, Bob's measurements, and we basically just needed to worry about the information that Alice can signal to Bob in her states. So the statement on the left side was sufficient. Now in our case, it's a little bit more complicated, because we still have the same thing for Alice. So we need to make sure that Alice's states cannot signal to Bob or Charlie, and we can basically do that using exactly the same trick. But we now also need to make sure that Bob cannot signal to Charlie, and especially Bob cannot signal to Charlie and Alice combined, because it could be that Alice and Charlie in some sense are cooperating. Alice is preparing a specific state, Charlie's performing a specific measurement. they might even share entanglement that would allow them to extract some information about Y, and that is something that we need to handle in this case. So essentially, what we're doing is we're generalizing this for quantum instruments, and we're doing this both for where we have polynomials in Charlie's measurements, as well as well, some kind of block encodable operators that correspond to Alice's states on the right side. Right. So we have all of these block encodable stuff, both before and after the quantum instrument. And so this somehow corresponds to saying there is no information about the about Y that's leaked through the quantum instrument that's accessible from, you know, like sandwiching this quantum instrument with algebras on both sides. Somehow an algebra generated on the right and an algebra on the left generated by Charlie's instruments.
Sorry, you know, like, can I ask a question? I mean, I know it's already like, Atul, you can stop me, you know, like, so basically, you know, like, so you said that, you know, it's like you're like making these polynomials, and as the degree of the polynomial increases, then at that point you approach the quantum set. But it seems like, you know, I mean, you are approaching the quantum set from the outside, right? I mean, because you said that, you know, at the for a small level, it's like no signaling, and then by increasing the degree, you are, you know, like, I mean, you are approaching the quantum. So let's say at some small degree, I mean, even if for a small degree you can show some soundness, then it will be soundness against a more powerful adversary than a quantum adversary. So in that sense, do you really need to increase the degree? Because, I mean, if you have soundness against a supra quantum adversary, because as in NPA, right? I mean, you are coming from outside, and it's not a, you know, like inner hierarchy, but outer hierarchy, you know. Like,
yeah, I mean, so in principle, you could do something like this, and what you're describing essentially sounds like the NPI hierarchy to me, which is saying that we are increasing the degree of the polynomials, and essentially what we're doing is we're by enforcing more and more of relations, more and more relations of this form here. What we're essentially doing is we're shrinking the set of correlations down from the no signaling to the quantum set, the quantum commuting operator set. Now you could stop somewhere before, but well, it depends a little bit what you mean with we get quantum soundness then, because so if we would only have conditions of this form for low degrees polynomials, then we couldn't translate it directly to, you know, a statement of this form here on the lower right, because this here we want to hold somehow in an algebraic sense. We want that this be these instruments that are implemented by Bob, that if we model them as maps between algebras, that they are now similar, that they're close. Now, this wouldn't be true for the entire algebra anymore, right? Because you only look at polynomials of a certain degree at most. So then maybe this would be true for some kind of subspaces of it. And I could imagine that you could try to derive, you know, map this back to some other kind of strategies that are super quantum. But since in our case, we're interested in mapping back to quantum strategies, we're we want to kind of go all the way and show this for the entire algebra. And actually, I mean, it holds. So what we're showing is that you can actually get this from the security of the QFHE scheme. So next step is taking the limit. So you want to take a limit in lambda. So for ground security parameter, and if you can click the thanks. So essentially, what we want to do is we want to take this limit, and the difficulty is that we somehow need to capture the fact that the Hilbert spaces in which the provers operate, they might be growing with a security parameter naturally. We allow the prover to perform larger and larger operations, and we actually need to do that because they'll also get longer ciphertexts. And so therefore, the space here on the left side on which the provers are operating, this is going to be given by some sequence of Hilbert spaces, which is growing in dimension. We'll get, for each of these lambda, we get a set of measurements, states, and transformations, and these correlations. We somehow need to be able to explain what it means to take a limit of all of these, objects. Well, then a nice way of doing this is moving to a C-star algebraic picture. So C-star algebras are another way of talking about quantum information, actually quite similar to the Hilbert space case, but somehow well adapted to the infinite dimensional setting. And especially what they allow us to do is they now allow us to move, basically to rewrite the prover strategies from the Hilbert spaces to translate it into the algebraic language in such a way that now the only thing that actually still depends on the security parameter lambda is going to be the state. So only the state is going to depend on it, and all of the other components, so the measurements which are living in the algebra, as well as Bob's transformations, they're going to be independent of lambda. So a little bit of a trick that involves universal C-star algebras. It's something that I'm going to get to now. Okay. Thanks. So essentially, what a universal C-star algebra is, in this case of PVMs, is it somehow abstracts from concrete PVMs. So if we have on the lower left, on something Hilbert space, we have PVMs, which are bounded operators given by bounded operators on this Hilbert space. Then the universal C-star algebra of PVMs allows us to somehow abstract from this picture by equipping us with a representation, this theta, that's mapping the algebra down into the concrete space of bounded operators on this Hilbert space, mapping the generators of this algebra to the measurement operators, the PVM elements of this concrete case. So this is what this is doing. And now the nice thing about this is that when before we were having Bob's measurements on the lower left, then Alice's states, which are essentially mapping these measurement operators to C by taking the trace of the product with it. Now, this can be lifted to this universal C-star algebra through the representation by having now measurements, the measurement operators live in this algebra, and having a state defined on it. So Alice's state, which is a functional of this into C, but just first representing and then taking Alice's strategy. So now, essentially, what this means is that since the C-star algebra on the upper left is universal, it's not depending. So the elements that are living there are not depending on concrete objects anymore, on lambda. And the only thing that depends on it is phi lambda, which is a composition of the representation and Alice's state, which essentially means that it will capture both the information about Alice's strategy and about Bob's strategy in the state. Okay, next. Now, okay, we're trying to do a very similar thing here, but we need to do it for more than two parties.
Dominik, sorry, but before you move on, I forgot you had explained why we're using PVMs and not POVMs. There was like some reason. Is it important at this point, or do you think it would be better
maybe I can explain it. Yeah, maybe I can explain it on the next slide.
Okay. Sorry.
Yeah, so it's a little bit. You're right. So it's easier to work with PVMs, and the reason is exactly because it allows us to draw this this commuting diagram here more easily. Okay, so essentially what we're doing here is the bottom line still corresponds to concrete strategies. On the very left, we have Charlie's measurement operators that lie in this BH lambda. Then we have Bob's strategy that's mapped as a quantum instrument, mapping measurements to measurements, and then Alice's state that's mapping this to C. Now we want to lift all of this again to the universe, like an algebraic picture using universal C-star algebras, to get rid of the lambda dependence in the spaces and the objects except for the state. And we're kind of kind of doing the same thing. And let's assume that we would have this commuting diagram already. Then basically this shows that we can lift Charlie's measurements to AC, which is the universal C-star algebra describing Charlie's measurements. We can then lift Bob's and Charlie's combined measurements, joint measurements, to this algebra in the middle, A, B to C, which is lifting exactly what was lying before in BH lambda. And maybe as a quick reminder here, in BH lambda, we weren't having, Bob's measurements, but actually what we have here, the objects that are living in there are Bob's and Charlie's joint measurements, right? Because in the lower left, we have Charlie's measurements. We apply Bob's instrument to it. So actually what we get here is measurements that have both of these labels. So we still have the joint measurements of Bob and Charlie, and that's what we're lifting. Now, exactly, to get to the PVM question, what we know something additional about these measurements that we're lifting, which is that they are sequential measurements, actually. So we know that Bob is acting before Charlie, or in this picture, we have Charlie's measurements and Bob's instruments pulling them back. And this imposes additional structure, which is, formally captured here on the right. And it turns out that if we're acting in C-star algebras of universal C-star algebras of sequential PVMs, we kind of get this map T that now connects the universal C-star algebras for free. And this is the main reason why we're looking at PVMs. So in the case where these universal C-star algebras of PVMs and of sequential PVMs are purified, so describing PVMs, there's a natural map between these two that's connecting these C-star algebras. And the nice thing is that this map is actually a star homomorphism, which essentially means that it allows us to think of the algebra that's describing Charlie's measurements as a subalgebra of the universal C-star algebra that's describing Bob's and Charlie's joint measurements. So in some way, this TBY is embedding AC into this algebra ABC. Okay, next. Thanks. Wait, maybe on the previous slide still? Yes, here, thanks. So so essentially what we can then do once we have all of the structure is we're using what we're knowing from before, from the block encodings and the conditions that we got from the cryptography. We're using this in this case to take the limits of these objects. Right now, after lifting everything into the universal algebraic picture, the only dependence on lambda is the state. So this phi lambda on the right side. That's the only thing that's left with a dependence on lambda. And it turns out that we can now use some compactness arguments in the space of functionals on this algebra to actually extract a subsequence in lambda for which those will converge in a weak star topology, which is going to be sufficient, though, to show that there is going to be a subsequence for which the correlations will converge. So the conditions that we get from this is that we can basically generate these limiting states and objects. So this limiting state phi ax, such that it's we actually get a perfect and idealized no signaling condition on this state. Okay, now we can continue. Basically, I described already what was written here. So basically, we use the constraints that we got from the crypto in the section before, and we use that the limit that we're taking behaves well enough under these constraints to give us in the limit an idealized version of them, which is that they are exactly that they're essentially perfectly the same. So the state phi for x and for x prime are going to be exactly acting the same in this algebraic picture. Okay. I think we can continue. Okay, so that basically brings us to the last part of the proof. So to recap, we've started with compiled strategies. We've thought of them as sequential strategies. We looked at what are the conditions, the algebraic conditions that we get from the cryptography. We lifted the strategies into an algebraic picture using universal C-star algebras, where we could take the limit in the security parameter, which idealized these conditions. And now essentially what we get is, and that's exactly what we have in the upper right corner of the picture, is we're having a sequential strategy where we have perfect no signaling condition in the communication between the parties. Okay, so at this point in the bipartite case, we're almost done, because there's this theorem which is called SGHAW theorem, because it was rediscovered a lot of times in quantum information, which is essentially saying that exactly in this situation, so you've got one party that communicates to another party, and the states that are the assemblage of states that's communicated satisfy exactly the condition that we have here on the left. This can be mapped back into a non-local picture, into a space-like separator picture, where they have a common resource and measurements on separate registers. So this is in the finite dimensional case. Now, in the infinite dimensional case, if we can continue a little bit to the exactly, so in the infinite dimensional case, there's an analog theorem of this, which is called the Radom-Nikodym theorem, which looks essentially the same, except for now we're not looking at density matrices, but we're looking at states on C-star algebras. And if we have a state that satisfies essentially the same condition, so a no signaling condition for the state with respect to the algebra, we know that we can represent it as a non-local strategy, but now not on separate registers, but on the same register and commuting operators. So now in the bipartite case, at this point we're essentially done, because we can use that we have this condition from before, and we can map it back to the non-local case. Now in our case, it's a little bit more difficult, because we've got more than two parties, and it's actually been kind of an open problem to understand what happens in this situation, especially because there are, so it's essentially this post-quantum steering phenomenon tells us that even though we impose no signaling conditions on the states that the parties communicate, this might not be enough this might not be strong enough to be able to map back to the non-local picture. So here that we have a little bit more, which is we have conditions on the quantum instrument that's implemented by Bob. So we know that Bob's quantum instrument is acting in a non-signaling way, and this will be in the end sufficient to map back, actually. So what we're doing is we're using a more general form of the Radom-Nikodym theorem, which is a version of the Radom-Nikodym theorem for completely positive maps in this case, which is what these quantum instruments are. So it's also often encountered as Belafkin's Radom-Nikodym theorem, and this is essentially telling us the same thing, except for now it's not replacing a state with a common resource and a measurement, but it's saying we're replacing a quantum instrument with essentially another instrument and a commuting measurement with it. If you've seen some of the C-star algebraic stuff before, on states this is very much related to the GNS construction, and for CP maps, this theorem is closely related to its Stein-Spring dilation. Okay. So if we use this theorem, which already existed in our case, we can apply now. We can apply it either to Alice and Bob's jointly prepared state, and we get the jointly prepared state replaced with a measurement, or we can apply it to Bob's measurement in this case, and what we get is a further factorization of this into basically Alice's. So we get a common resource, then Alice's measurement, Bob's measurement, and Charlie's measurement separately, However, there is a little bit of an issue, which is that there is this operator V, which is essentially a Stein-Springer symmetry in between. And so what this is saying is that we somehow have separated what these parties are doing, but still the operators are living in different spaces. So we have operators, but they're in different Hilbert spaces. So we didn't manage to make them use a common register at this point. And this was then the last technical difficulty that we needed to overcome. And essentially what we needed to do is we needed to show that this version of the Radon-Nikodym theorem for CP maps, which was known, actually also holds in a way in which it can be composed with itself. So if we have several applications of it to states or CP maps, what we need is that the kind of the measurements that we factor out by applying this theorem, we can still force them to all live in the same space, and especially to still commute in that same space still. So essentially, yeah, what we needed to do here is we needed to pull this measurement operator that's describing Alice's strategy and pull it into the larger Hilbert space in which Bob's measurements and Charlie's measurements are already living. Well, and so that's something that we did. So we have a result that allows us to do that, and basically what we got is a chain rule for this Radon-Nikodym theorem, for these Radon-Nikodym derivatives, which is saying that if you have a chain of states and CP maps that satisfy these properties, these no signaling properties, then actually in the end you get a collection of measurements that describe the different parties, and all of them will be living in the same Hilbert space, potentially infinite dimensional Hilbert space. And in this space, they will also be all pairwise commuting. And we've actually got like a slightly more general version of this chain rule as well in an entirely algebraic sense. Well, okay, and then putting this all together, this basically completes the proof, because this was the last missing piece at the top. And using this chain rule, we can now map back to commuting operator strategies. So maybe if you click once more, we have the brackets. Yes, thanks. So we map back into the case where all of these parties are implementing commuting operators on the same register. And as I mentioned, so what I was talking about, all of these tools for three parties, actually kind of the focus of this was to do it composably. So we did this for quantum instruments. You can compose all of them. So this block encoding results that we have, they're composable. We have a composable construction for these universal C-star algebras of sequential PVMs, and we show that they actually form a hierarchy. So you can keep embedding. Every time you add a party, you can embed this into an even larger algebra that contains all of the information. And then eventually we've got this chain rule, which is essentially a composition result for Radon-Nikodym. And using all of this, you can immediately then do it for an arbitrary number of parties. Okay. So this gives us the asymptotic quantum soundness for all multipartite games. And therefore it's kind of filling in the missing piece. Mainly what we've done technically is we have a lot of new techniques to treat quantum instruments. So these block encoding techniques, which are essentially capturing the restrictions that cryptography imposes on quantum instruments, which I think will be very useful also beyond this, because it just generally allows us to describe quantum instruments that are acting on encrypted information. And maybe open questions are, and let's start at the back. What we're mapping to at the end is quantum commuting operator strategies, although we started as strategies that were living in tensor products. So one can ask, of course, if this gap is naturally there, if this is optimal or if this is an artifact of the proof. And this is, as far as I know, not solved yet. So this is an open question that we remain interested in. If anybody else wants to work on this as well. And the other question is essentially about the convergence speed. So making this a little bit more quantitative. Since our result is only talking about asymptotic security, similar to the bipartite result that there was before. So this is saying nothing about how fast it converges. Essentially, it's telling you it doesn't tell you how you need to choose the parameters, the security parameter of your cryptographic scheme to reach a certain level of security, or to make sure that you keep correlations contained in a certain set. These are not statements that we can make quantitatively. But there have been now follow-up works in the meantime that have first treated this in the bipartite case and then also in the multipartite case. And these are actually the results that then rely on characterizations of these strategies using NPA hierarchies. So then maybe I stop here.